Hey everyone, and welcome to this explainer. Today, we are exploring an absolute masterpiece of software engineering. We're going to be looking at the Google File System, or as it's commonly known, GFS. This is literally the iconic blueprint for modern distributed block storage. It's the foundational architecture that figured out exactly how to take thousands of cheap, highly unreliable commodity hard drives and somehow fuse them together into a single exabyte-scale powerhouse. Seriously, if you want to understand how modern cloud storage actually works beneath the surface, you absolutely have to understand GFS. Let's get into it.
Okay, so here is our roadmap for today. We'll be hitting 1. Design goals for web scale. 2. The decoupled architecture. 3. The write pipeline. 4. The read pipeline. 5. Auto healing and resilience. And finally, we'll wrap up with 6. System bottlenecks and limits.
All right, starting with Section 1, Design Goals for Web Scale, Building Resiliency in Software.
To really wrap your head around GFS, you first have to understand its foundational philosophy, which is essentially assume the worst. You see, in traditional enterprise storage, companies would buy these incredibly expensive hardware rigs with all these built-in redundancies. Well, GFS completely threw that playbook out the window. The system was designed under the strict, uncompromising assumption that commodity hardware will always break. I mean, physical node crashes, network drops, and silent disk sector decays, what we call bit rot, they aren't treated as rare emergencies, they are treated as standard, everyday realities. Because hardware failure is basically the norm here, all the resiliency is moved entirely into the software layer. That requires automated, software-defined auto-healing to just gracefully handle failovers without a human ever having to intervene. Now, to optimize for those massive MapReduce datasets, GFS had to make two really crucial trade-offs. First, there's a heavy prioritization of high throughput over low latency. Standard transaction locks? Yeah, those are totally bypassed in favor of these massive, direct data streams. Second, think about the file structure itself. The datasets we're talking about are huge, multi-gigabyte files. So rather than trying to support random access overwrites, which notoriously cause massive lock contention, GFS is explicitly optimized for sequential record appends. You literally just keep adding data to the tail end of the file. That's it. It's a brilliantly simple approach that completely bypasses single-node transaction bottlenecks and allows multiple clients to just append concurrently without stepping on each other's toes.
Moving on to Section 2, the decoupled architecture, separating control from data.
So this is the radical architectural shift that made horizontal scaling actually possible. I like to think of GFS as a busy airport and a shipping port combined into one. The GFS master, sitting up top in the control plane, is basically your air traffic controller. It's a single node that just maintains the namespace directory indexes in its volatile memory cache. It doesn't actually touch the data itself. Down below, in the data plane, you have the dense OSD chunk servers. Think of these guys as the autonomous cargo ships. They're the ones hauling the massive raw data payload containers. By physically separating the metadata directory mappings from the actual raw file payload streams, clients can just get their directions from the master and then stream their bytes directly to the chunk servers. It totally removes the master from the heavy lifting, which is a total game changer.
And you really have to appreciate the extreme efficiency of the master's memory here. Get this, the master requires only a microscopic 64 bytes of RAM per chunk to store its metadata state. To put that into perspective, a massive 100 terabyte data store requires only about 100 megabytes of master RAM. That is wildly efficient. Also, look at how GFS handles file paths. Instead of those deeply nested, recursive directory trees that really bog down search times, it uses a flat key-value path hierarchy with coarse-grained locks. For example, if a client wants to mutate the path A/B/C, the master just drops read locks on A and A/B and a write lock on C. Boom! This totally eliminates recursive search overhead and prevents race conditions pretty much instantly.
Now, the fundamental unit of allocation in GFS is called the chunk, and it is massively fixed at 64 megabytes. You might be wondering, why so huge? Well, because it minimizes the master's memory footprint and allows the clients to easily cache locations. But honestly, the real genius here is the stateless offset math. When a client wants to read a file at a very specific byte offset, its CPU just uses rapid floor division math. It literally just divides the offset by 64 megabytes. This translates the logical query directly into a chunk index and a unique 64-bit chunk handle. By doing this, the client completely bypasses slow directory tree scans, saving a massive amount of compute time, and it knows exactly which specific block it needs to ask for.
All right, let's get into Section 3. The write pipeline, orchestrating exabyte streams.
Okay, we are now shifting to what is arguably the most complex mechanism in this whole explainer, the high-speed data write flow. The absolutely crucial point to understand is how GFS manages to achieve massive throughput safely. It does this by decoupling the network payload streaming from the actual local write serialization. And it pulls this off using temporary, volatile leases. The master will grant a 60-second lease to one specific replica, making it the primary. So the network data streams across all the replicas in a daisy chain, but the actual command to finally commit that data is tightly orchestrated by that single primary leaseholder.
Let's actually walk through this incredible 9-step mini-narrative so you can see it in action. First off, the client asks the master for the replica locations. The master grants the lease and replies. Then the client starts streaming the raw data into a pipeline daisy chain, just buffering it in the chunk server's RAM. Notice that. It does not write to the disk yet. Once every single node acknowledges they have the data buffered, the client dispatches a formal execute write command to the primary chunk server. The primary serializes the sequence, forwards that commit command to the secondaries, they all flush the data to disk simultaneously, and finally, a unified success acknowledgement makes its way right back to the client.
Let's focus in a bit closer on that primary chunk server's role, because it acts as the absolute authoritative engine here. Imagine multiple clients are all trying to append data to the exact same block at the exact same millisecond. To prevent total chaos, the primary assigns monotonic sequence numbers. So think like transaction 42, then transaction 43, to these concurrent updates. It commits the changes locally and then broadcasts that exact sequence downstream to the secondary replicas. This completely guarantees that all replicas commit the identical data boundaries in the exact same order, and it does it all without needing heavy system-dragging synchronization locks.
And this setup is exactly why GFS uses a daisy-chained pipeline instead of parallel writing. Think about it. If a client tries to push data to 3 replicas all at once, its 1 gigabit outbound network card is going to hit a severe egress bottleneck. It basically divides the bandwidth to 333 megabits per stream, which is incredibly slow. Instead, GFS uses pipelining. The client uses its full 1 gigabit capacity to send data to the first node. Then, that node uses its own independent capacity to forward it to the next. Plus, looking at the network topology, GFS utilizes proximity-based routing. The client streams to a node right in its own local rack, taking advantage of ultra-fast intra-rack loopback switches. This totally offloads heavy replication traffic from the central data center core network.
To make this pipeline even faster, lightning fast really, GFS takes that massive 64 megabyte payload and splits it up into 64 kilobyte micro packets. Notice how these packets overlap in transit. While packet 3 is just leaving the client, packet 2 is already hopping between servers, and packet 1 is actually finishing its journey. Mathematically speaking, because the total chunk size is so massive compared to the tiny network hop delay, this overlapping compresses network transit delays dramatically. The total transit speed actually approaches the maximum capacity of a single network link. It is a highly aggressive networking trade-off, but it absolutely maximizes continuous stream bandwidth.
Moving right along to Section 4, the read pipeline, direct binary sweeps.
Now, after all the complexity of writing data, reading it is contrastingly simple. It's really elegant. This 7-step flow perfectly highlights how GFS protects the master node from getting overwhelmed. The client asks the master for the chunk handle and the replica locations. The client then caches this mapping metadata locally. And honestly, this is huge. It means all subsequent disk seeks within that 64 megabyte boundary can fetch raw byte payloads directly from the nearest chunk server. The master is completely out of the loop at that point. Before the chunk server actually returns the data, it runs a quick checksum validation, which we are going to look at next, and then just streams the raw payloads straight back to the client.
Section 5, auto-healing and resilience, the system's immune response. Remember our very first design goal? Commodity hardware fails. So here is exactly how the system dynamically defends its data integrity against the inevitable reality of silent mechanical failures. Physical hard drive platters degrade over time, which causes bits to just flip randomly. To catch this, chunk servers divide their 64 megabyte blocks into smaller 64 kilobyte sectors, and each one is stamped with a 32-bit CRC checksum. When a client requests a read, the chunk server dynamically recalculates that signature right in memory before ever sending the data. If the recalculated checksum doesn't perfectly match the stored record, boom, it's caught. The chunk server immediately drops the corrupted block, returns an error to the client, and reports the rot to the master. The client, meanwhile, just seamlessly redirects its read to a healthy replica.
And this right here builds an incredible automated recovery loop. Once that bad block is deleted, the chunk server's regular heartbeat check-in to the master is going to show that it's suddenly missing data.
The master detects that the replication density for that chunk has dropped from 3 down to 2. It instantly updates its internal maps, evicts the bad replica pointer, and schedules a dynamic replicate task. It essentially instructs the degraded chunk server to backfill the missing data by opening a direct, asynchronous TCP stream straight to a healthy peer node. So the master orchestrates the repair, but the actual heavy data lifting happens directly between the worker nodes themselves.
Of course, we have to ask, what if the master itself crashes? To ensure control plane availability, the master continuously records all namespace changes to a physical operation journal, which is synchronously replicated out to standby masters. But if a crash happens, replaying billions of log records from scratch would literally take hours. So the active master takes periodic memory snapshots or checkpoints. If the active master suddenly dies, a standby boots up, loads the latest checkpoint directly into its RAM, quickly replays just the trailing journal updates, and assumes complete active control in under 5 seconds. I mean, the system barely even blinks.
And finally, Section 6, System Bottlenecks and Limits, the irony of scale.
This brings us to the dramatic twist of our explainer. The exact design choices that made GFS and exabyte scale triumph ultimately became its fatal weakness, as Google's own workloads evolved. You see, GFS was originally built for a few massive files, but then came applications like Gmail, which started generating billions of tiny files. Because of that rigid 64 megabyte chunk size, we saw severe internal storage fragmentation. A tiny 10 kilobyte email still consumed an entire 64 megabyte chunk allocation slot, essentially wasting 99.9% of the physical sector space. But the real killer? Every single one of those billions of tiny files, even though they were mostly just empty space on the disk, still required that 64 bytes of mapping memory in the master's RAM. Eventually, the in-memory namespace registry hit an absolute hard single-node RAM cap. The master literally ran out of memory, choking the entire system under the weight of microscopic files, despite having petabytes of empty hard drive space left over.
And that leaves us with a really fascinating puzzle to ponder. GFS definitively proved that brilliant software could conquer unreliable hardware, but it ultimately hit the physical limits of a single machine's RAM. So, if the centralized master's memory was eventually defeated by billions of small files, how do you think Google's next generation of cloud storage, modern systems like Colossus, reinvented the metadata layer to shatter this ceiling? Think about how you might distribute the control plane itself to solve that. It's a great problem to think through. Anyway, thank you so much for joining me on this deep dive into the Google file system. Keep exploring, and I'll see you next time.